Hello, everyone. Welcome back. We are starting chapter 4, and chapter 4 is all about probability. This video will cover section 4.1. So we're going to go through some basic concepts of probability. In probability, an experiment is any process with uncertain results that can be repeated. Now, I want to emphasize that is a very important point. That can be repeated. If something can't be repeated, then we don't consider the experiment valid. So when scientists do experiments all over the world, they post to everybody exactly what they did and how they did it and what they used and what materials and everything, so that other scientists around the world can repeat it and hopefully get similar results. If no one can repeat the results, then it's considered a bad experiment and not accepted. The law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of that outcome. Basically, what this is saying is, if I were to flip a coin 10 times and I got heads 3 of those times, then that would be 30% of the time I got heads. Now, flipping a coin 10 times and getting 3 heads, that's not that unusual. Even though we know that 0.3 or 30% is not the true proportion, the true proportion should be 50%, because half the time I should be getting heads, half the time I should be getting tails. But if I did the flip the coin thing 10,000 times, then most likely it's going to get closer and closer and closer to 50% of the time it was heads. That's the law of large numbers. So if we just keep doing it over and over and over again, we should eventually get to the true probability. We have a few definitions we need to get through. We're going to start with a sample space. Sample space. We often call that S of a probability experiment is the collection of all possible outcomes. This is all possible outcomes. So if we take, say, a die, that's a single dice, a 6-sided, then our entire sample space is 1, 2, 3, 4, 5, or 6 on a single roll. This is all of it. It's never going to be a 7. It's never going to be a 0. It's never going to be a -2 or anything like that. This is the entire sample space for rolling a single 6-sided die. Next up, we have an event. Is any collections of outcomes from a probability experiment. Events may consist of one outcome or more than one outcome. And we often use E, F, G, H to represent the events. Normally, the events, we like to write out in words what the event is. It makes it a lot more clear for other people who are reading it. And we'll see what we mean by that in a minute. But I want to get to unusual events. Unusual events is an event that has a low probability of occurring. And typically we say less than 5%. And that's sort of a standard that we're going to go on in this class, although in real life, you would need to set your own level. And we'll get to all those other definitions as well. Next up, a probability. Model lists the possible outcomes of a probability experiment and each outcome's probability. We'll explain what more that means in just a moment. So here's some rules of probability. P of E, the probability of event E occurring, is what that means. P of E is always between 0 and 1 inclusive. And what we mean by the word inclusive is that it's possible to get a 0 probability, and it's possible to get 1 for a probability, meaning 100%. If an event is impossible, then the probability is 0. If an event is a certainty, then the probability is 1 or 100%. Those ones are usually pretty boring. We're more interested in ones where it's not 1 or 0. So let's start by interpreting our statement here. It says the probability that an individual walks to work is 0.03. Now we would say that that is 3%. 0.03 is 3%. And this would mean that if we survey 100 individuals, we would expect about 3 to walk to work. That's what we mean by that. All right, let's do a tree diagram is our next area of focus. tree diagram. So we can get kind of a handle on what we mean by sample space. If a basketball player shoots three free throws, describe the sample space of possible outcomes using S for a made free throw and F for a missed free throw, meaning S is successful, F is a failure. What is the sample space? So what is the size of the sample space? So we're going to draw it with a tree diagram. So in the first shot, the basketball player could successfully make it or not make the first free throw. For the second shot, he or she could be successful or could fail it. And for the third free throw, they could be successful or they could fail. This is the entire space, and I'm going to write it out. So here are the four possible outcomes if they make the first shot. And if they miss the first shot, it's going to look like this. And this is the entire sample space. This is every possible outcome of 3 free throws. And you'll note at the end, when we count all these up, we have a total of 8 possibilities. So this is how a tree diagram can help us kind of see what our sample space looks like. All right, let's do another one. If a person rolls a 4-sided die and then flips a coin, describe the sample space using 1, 2, 3, or 4 for the die outcomes and H and T for the coin outcomes. And then again, we'll talk about what is the size of the sample space. So when rolling the dice, they can get a 1, a 2, a 3, or a 4. Those are the only options. Then when they flip a coin, they could get a heads or tails. And these outcomes are going to look like this. This, once again, is the entire sample space of rolling a 4-sided die and flipping a 2-sided coin, obviously. And it looks like, once again, our sample space is 8. There's not a pattern here. These just both happen to be 8. And eventually we'll learn how to compute that without having to write everything out like that. We have 3 methods to determining probability: approximating using the empirical method, computing using the classical method, which is what we're going to focus on. And then the subjective method is when people just guess. So that's like a terrible method. So let's focus on this and go straight to our example here. A number cube with faces labeled 1 to 6 will be rolled once. So this is a die. The number rolled will be recorded as the outcome. Give the sample space describing all possible outcomes. Then give all the outcomes for the event rolling a number 3 to 6. All right, so our sample space is going to look like this. It's going to be 1, 2, 3, 4, 5, or a 6. And when you type that into ALEKS, you'll just click right where the cursor is, and you'll just type using commas. And the event of rolling a number 3 through 6, you'll note what's the probability of rolling that, and that is 4 numbers. That's 3, 4, 5, and 6. That's 4 numbers out of the 6, which is 2/3. And they don't say that they want it as a fraction or a decimal, so we'll approximate it as well. When you divide that out, you get 0.6667, which is about 66.67%. So not too bad. A survey of 500 randomly selected high school students determined that 288 played organized sports. What is the probability that a randomly selected high school student plays organized sports? So the probability plays sports. And this is what I meant by we usually write it out instead of calling it event E or something like that. Well, I know for sure that my denominator is going to be the 500. That's the total number of high school students that are there. And out of those 500, 288 of them played organized sports. So if I were to divide that out, 288 divided by 500. So this is actually exactly equal to 0.576. That is my final answer. Which would mean, if I wanted to write it as a percent, which it does not say to do, but if I wanted to, this would be 57.6%. And a box contains 10 cards labeled J, K, L, M, N, O, P, Q, R, and S. So let's see how many letters that is. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 letters. All right. One card will be randomly chosen. What is the probability of choosing a letter from N to Q? So let's count those out. 1, N to Q. 1, 2, 3, 4. So that is going to give us, so the probability of N to Q is going to be 4 out of the 10. Which you could just type 4 over 10 into ALEKS, that's fine, but hopefully you see that that reduces to 2/5. Again, ALEKS will accept non-reduced answers. And your teacher may as well. You'll have to ask your teacher. All right, next up, in an aquarium, there are 6 large fish, 8 small fish, and half of the large fish are blue. So before I get going, just to keep this straight, half the large fish, there's 6 large fish. This means that 3 large fish are blue. One fish is selected at random. Find the probability that it is a large blue fish. Okay. So the probability, large and blue. First off, how many fish are there in the tank total? There is 6 plus 8. That's a total of 14 fish. And how many of them are large and blue? Well, we already figured out that's half of the 6. That's going to be 3 out of the 14. And they say leave it as a fraction, and this definitely does not reduce. There you have it. Next up. A coin is tossed 3 times. An outcome is represented by the string of HTT, meaning first was heads, then the next 2 were 2 tails. The 8 outcomes are listed on the table. Note that each outcome has the same probability. For each of the 3 events on the table, check the outcomes that are contained in the event. That's there on the left. Then the last comment enters the probability of the event. Okay, so event A here. A tail on both the first and last tosses. First and last tosses. We've got that there. We've got that there. And that's it. So that means that's going to be, there's a total of 8. So n in this case is 8. Meaning 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be my denominator. And in this case, there are only 2 out of the 8, which is 1/4. Event B, a tail on the last toss. All right, let's use a different color here. Tail on the last toss. We have one here, we have one here, one here, and one here. So that's looking like 4 out of the 8 to me, which is half. Event C, a head on each of the last 2 tosses. All right. An H on the last 2 tosses. We have that here. We have that here. And that is it as far as the last 2 tosses go. That's it can be 2 out of the 8, which again is 1/4. Not too bad. All right. The state lottery board is examining the machine that randomly picks the lottery numbers. On each trial, the machine outputs a ball with one of the digits 0 through 9 on it. The ball is then replaced in the machine. That's important to know that it is being replaced. The lottery board tests the machine for 25 trials and got the following results. So this says that, just to interpret this table that we see here, how often did a 0 come out? 3 times. A 1 came out 7 times, a 2 came out 1 time, a 3 came out no times, a 4 came out 4 times, a 5 came out 3 times, and so on. And if we were added up the number of trials that you see there, it should be 25, and it is. So my denominator is going to be 25 for sure. From these results, compute the experimental probability of getting a 4. Okay, so there were 4 4s out of the 25. So 0.16. Part B. Assuming the machine is fair, compute the theoretical probability of getting a 4. Well, there's 10 numbers, and they should all have the same probability. So there's 1 4 out of the 10. So that's going to give me 0.1. Part C. Assuming that the machine is fair, choose the statement below that is true. With a small number of trials, it's surprising when the experimental probability is much greater than the theoretical one. I don't think so. With a small number of trials, it is not surprising, I would agree with that, that the probability is larger. So I'm going to go with that one. And the last one, with a small number of trials, the experimental probability will always be much. That's not true. It's not surprising that they're quite different because it was only 25 trials. If we did 100,000 trials, then I would expect it to be closer to the 0.1. All right. That's kind of small. Let's make that bigger. In the Venn diagram below, C and D are events in the sample space S. So we're going to shade in the event, and let's define some of these. So part A says shade C intersection D. Intersection is the part where they overlap. So I'm going to shade in the area where they overlap, and that's just here. Now, when you're doing the homework, you'll have a tool where you can just click in the right place and it'll fill it in for you automatically. And to be clear, this means C and D. This here means C or D. And I know that seems the same, but it is not. C or D means it's everything, including the overlap. So you would shade in all 3 of these regions here. Venn diagrams. We like Venn diagrams. Here's another one. A pet store surveyed 178 people to see how many own a dog and how many own a bird. The Venn diagram below shows the results. All right, part A. And let's talk about this Venn diagram for a second. So own a dog is going to be everybody in that circle. So that's going to be the 37 plus the 39. Looks like I'm actually got my calculator ready here. How many of them own a bird? Well, that's going to be the 39 plus the 28. So that's going to be 67. That's the 39 plus the 28. How many of the people own a bird or a dog or both? So that's going to be the 37 plus the 39 plus the 28. 37 plus 39 plus 28. I'm getting 104. How many of the people do not own both a dog and a bird? So meaning we don't want the 39. We want everything else. That's going to be 37 plus 28 plus 74. Now the 74 represent people that don't have a dog or a bird. So we're only excluding those who have both a dog and a bird. So I'm getting 139. All right. And that brings us to a subjective probability. And that's based on personal judgment, which of course is completely useless. So if someone says 80% of the people agree with me, you stop and you say, hey, that you're just making that number up. Why would I believe you at all? It's totally subjective. So we try to avoid that the best that we can. And here we have a deck of cards. Those of you unfamiliar with a deck of cards, there are what are called 4 suits. The suits are clubs, diamonds, hearts, and spades. 2 of the suits are black in color, and 2 of the suits are red in color. Each suit has 13 cards. The first 10 are labeled 1 through 10, except the one we don't call it a 1, we call it an ace. And then there are 3 what are called face cards. That's the jack, the queen, and the king. Now that's going to make up 13 by 4, which means our sample space here total is 52 cards in a deck of cards. All right, so our denominator is going to be 52 for each one of these. So we'll start with part A. Red queens. So let's highlight that. Here's a red queen, and here's a red queen. So there are 2 red queens. Out of the 52. And it says to leave it in reduced fraction form. That's going to reduce to 1 over 26. What's the probability of drawing a face card? Well, again, my denominator is going to be 52. How many face cards are there? Well, there's 3 in each suit, and there's 4 suits. So 3 times 4 is 12. And that is going to reduce to, so 12 divided by 52. And I'm going to hit math and convert to a fraction. It reduces that to a 3 over 13 for me. And that is going to reduce to 3 over 13. Part C. Probability of a diamond. Well, how many diamonds are there? Well, that's just 1 suit, so that means that there's 13 out of the 52, which is going to reduce to 1/4. Meaning I have a 1 in 4 chance of drawing a diamond out of a 52 card deck. All right. Part E. Part E says, we did D, pardon me, not E. Part D says 2 of clubs. Well, how many 2 of clubs are there? There's exactly 1. 2 of clubs is right here. So that means that we have 1 out of the 52. Part E, black cards, probability of black. Well, half of them are black, so that's 26 out of the 52, which reduces to 1/2. In part F, green cards, so probability of green is going to be 0 out of 52, which is just 0, meaning we're not going to get a green card from a standard deck of cards. Well, I hope that you found that useful.